Let me introduce today's speaker, Toshi. Um, Toshi is a postdoctoral fellow at the Lawrence Berkeley National Lab and works on water, energy, and chemical transport in soils using numerical modeling as well as machine learning. He completed his BS from University of Tokyo in Japan, and then he came over here to UC Merced. I have known Toshi for over a year now, and he is a deadly combination of two things. He's one of the most genuine person you'll ever meet, and also he's one of the most sound researchers I've ever seen, and which I'm hoping you will all witness in the next 2 hours. Having said that, I'll leave it over to you, Toshi.
Mhm. All right. Yeah. Thank you so much for the introduction. Maybe it was very, too nice for you. It was a very nice introduction. Thank you so much. And also thank you for the invitation. Okay. So let me share the screen with you guys. Can you see my screen well?
Yes.
Devashish?
Yes.
Okay. Sounds good. Okay. Hello, everyone. I'm Toshi from Lawrence Berkeley National Laboratory. I'm very excited to teach you how to implement differentiable modeling with implicit differentiation. Before getting into the technical details, let me introduce myself a little bit. The slide doesn't work. Okay, here it is. Okay. I'm a computational solid physicist. Then my research is primarily focusing on the integration of model and data. I'm originally from Japan, then did bachelor's and master's program at the University of Tokyo in Japan. Then I moved to the States to get the PhD from University of California, Merced. Then I'm currently a postdoc at Lawrence Berkeley National Laboratory. In terms of research, I pretty much focus on computational work, though I did some experimental studies during my master's program. Since my PhD program, I have developed some physics-informed machine learning methods for Bedostone hydrology, and I'm currently working on reactive transport models. Here's the overview of the lecture today. Today, we have a very ambitious goal. Then I will let you do a lot of work, so kind of be ready. Firstly, I will talk about our latest research on integrating neural networks into physics-based models to analyze soil moisture data. Then during the coding session, we will learn the three main technologies or methods used in the study to implement differentiable modeling for implicit models. These methods are gradient descent methods, Newton's method, implicit differentiation. All the three methods are very general and used everywhere in science and engineering, so you never regret learning them. During the coding session, we don't use any machine learning framework, and instead, we implement everything from scratch. After the coding session, I will quickly introduce a machine learning framework called JAX I'm using to implement the same methods much easily. Then I will share some resources and conclude the lecture. If you have any questions, please put the questions into the chat. I will try to answer as many questions as possible during the coding session and also after the lecture as well. Okay, so let's move on to the introduction. This introduction is based on our latest research, JAX accepted by Water Resources Research last week, actually. I put the accepted manuscript into the Google Drive folder. So please read this if you are interested. Before talking about the details, I would like to acknowledge the funding sources and also the collaborators. This study was funded by the US Department of Energy through the ExaSheds project. I'm also funded by a RE Carrier grant from the Lawrence Berkeley National Laboratory. Okay, so let's move on to the research part. The research question in the manuscript is quite simple. How can we improve our ability to extract information from soil moisture data like this? For example, we have images of laboratory infiltration experimental data taken by shortwave infrared camera. By the way, these experimental data are provided from the University of Arizona and Utah University. Here, the water is entering into a dry soil from the bottom and moves upward. How can we analyze this type of data, for example? Of course, the first step is to plot the data. It's very important to plot raw data before analyzing it using any models or sophisticated methods. In the right figure, I plotted the soil moisture estimated from the images at different depths. The x-axis is the time and the y-axis is the water content in the soil. Different colors represent soil moisture at different depths. For example, this point represents the soil moisture estimated at near the bottom, and this one is measured at near the top of this soil column. All right. Then okay. Initially the soil was very dry like this. Then the water content was very low at all the depths, but once the wetting front reaches, the soil moisture increases from the bottom to the top location. Also, the slope of the breakthrough curve differs from location to location. Okay, it's good to begin with this type of uh, qualitative analysis, but we would like to analyze the data more quantitatively. There are many methods to do that, but one of the basic approach is to use physics-based model for soil moisture dynamics, which is the Richards equation I will introduce in the next slide. The Richards equation is based on the conservation of mass and Darcy law for unsaturated flow. In this partial differential equation or PDE model, theta is volumetric water content in soil. Psi is the potential energy of water. K is permeability, Kr is relative permeability, and there are three other physical constants. What the equation says is that the change in the water content is equal to the gradient in the water flux, and water flux is the product of this hydraulic conductivity and the gradient of potential energy. Then the potential energy has two parts. The first one is the water potential of soil. This is because of the soil matrix. And the second part is due to the gravitational energy potential. Okay, this is the brief introduction of the Richards equation. Okay, so this slide shows a comparison between the experimental data and physical model. The left figure is the experimental data, and the right figure is the numerical solution to the two-dimensional Richards equation. The numerical solution is qualitatively similar to the experimental result, but there are some differences, such as the speed and the heterogeneity of the water movement in soils. To make the physical model useful, we need to calibrate or tune some of the parameters in the physical model or the Richards equation. Then I'm introducing the general framework to do that, which is inverse modeling. Inverse modeling is a systematic framework to fit physical models to data. For example, we have the Richards equation to describe water flow in soils. To get the simulation data, we first solve the Richards equation with some parameters. Then parameters can be initial and boundary conditions, also can be soil parameters or soil hydraulic functions. Then given these parameters, we solve the Richards equation with any numerical methods, such as finite difference, finite volume methods, to get the simulation results. Then we compare the simulation with observational data, then take the difference as an objective function. We minimize this objective function to optimize the parameters. Then this minimization is usually done by gradient-based methods, which we are using today. Okay, so in this manuscript, we were focusing on calibrating soil hydraulic functions. Okay, so let's move on to what we did. Okay, so in this manuscript, we calibrated two functions in the Richards equation. The first equation is the function of water content of water potential, this function. And the next function is the relative permeability function, Kr of Psi. Let me introduce the first function first. This relationship between volumetric water content and water potential is called the water retention curve, which represents the water holding capacity of soils. As this figure shows, water can be captured between spherical particles. When the water potential is low, water content is low. Then when the water potential is high, water content is high. Although this example is very simple and real soils have much more complex pore geometries, we still can measure this water holding capacity by laboratory experiments that are shown in the pink points in the right figure, where the x-axis is the water potential and the y-axis is the water content. You can see that when the water potential is low, water content is low, etc. But from the numerical simulation point of view, we need to have some parametric model to describe the data well. One of the commonly used parametric model is called the Bang-Newton model, which is shown in the black curve like this. You can see the model is fitted to the experimental data quite well. So this model is widely used anywhere in the fields. Okay, let me move on to the next function, which is the relative permeability function. This function represents the water conductance property of soils. Although we can measure this function experimentally, we commonly use a bundle tube model or the physics-based model to get the function from the water retention curve. So in this physics-based model, we assume that soil is composed of different size of tubes like this and this and this, right? Then for a narrow tube, which is corresponding to low water potential, the relative permeability is low. For a wide tube, which corresponds to high water potential, the relative permeability is high, etc. Then once we sum up all the different tubes with different sizes, then we can get the relative permeability function, which is shown in the right figure, where the x-axis is the water potential and the y-axis is the hydraulic conductivity, which is basically this term, the whole term. But this hydraulic conductivity has the same shape as the relative permeability, so it's okay. So you can see that hydraulic conductivity drops dramatically as soil gets dry by several orders of magnitude. This is one of the reasons why the Richards equation shows a very nonlinear behavior. Okay, so let me move on to inverse modeling. In our manuscript, we consider inverse problem where we estimate Bang-Newton model parameters to fit the Richards equation to soil moisture data. As I described, the water retention curve and relative permeability function is parameterized by the Bang-Newton models. Then the goal of the inverse modeling is to estimate the Bang-Newton model parameters by minimizing some objective function L, which is basically the difference between the model output and data. Okay, let's see the result first. Okay, so here's the result for the inverse modeling when fitting the Richards equation with the Bang-Newton model. In the right figure, the x-axis is the time and the y-axis is the water content. Then, okay, these are the experimental data I described before. Then the numerical solution with the Bang-Newton model are shown by the dotted line. Although the numerical solution really describe the experimental data good enough, but there are some differences between the data and the model. For example, the fitting was not very good when the water content is very high around here. Also, at the beginning of the breakthrough curve, there are some differences like this. Okay, so in our manuscript, we propose a way to improve our ability to fit the numerical solution of the Richards equation to this data set by integrating neural networks. In our approach, we use physically constrained neural networks to represent water retention curve and relative permeability function. In this way, we increase the flexibility of our physical model, but at the same time guarantee the basic physics, such as the Richards equation, the conservation of mass, and the Darcy law in the Richards equation. Then we estimate the neural network parameters by minimizing the objective function like before. Okay, let's see the result. Here is the result for the inverse modeling. In the right figure, the fitted numerical solution with neural networks are represented by the solid curves like this. You can see the fitting was better for the neural networks compared to the traditional Bang-Newton model approach. This is because of the flexibility of the neural networks. Okay, so far so good. But the question is, how did we implement this method? So integrating neural networks into physics-based model is not really simple. Okay, so so before I talk about the implementation, I need to talk about one more result. This slide shows the estimated functions by neural networks. Then we show that estimated estimated functions are more reasonable than the traditional Bang-Newton model. In the left figure, the x-axis is the water potential, y-axis is the barometric water content. This is water retention curve. Yeah. Then the water retention curve estimated by neural network are represented by blue curve, and the Wang-Newton model is pink curve. We also plotted experimental data that were measured independently from the infiltration experiments. These are the data points. You can see that estimated function by neural networks are more aligned with the experimental data compared to the Wang-Newton model. So we demonstrated that by using neural networks, we can extract more information from experimental data. In today's coding session, I will teach you some of the methods we use to implement this research method. Okay, so to integrate neural networks, we implemented numerical methods to solve the Richards equation on a machine learning framework called JAX. There are a couple of techniques used in the study. First, we solved the Richards equation with a finite volume method. Then nonlinear systems from the finite volume is solved by the Newton's method. Then to train the neural networks, we implemented the gradient calculation algorithms through the nonlinear solver with implicit differentiation. Then we use the gradient to optimize the neural network parameters. It's okay if you don't understand any of them. I will explain these three methods in the coding session using a very simple toy problem. So after the lecture, I hope you kind of have a good understanding of what we did in the manuscript. Okay, so let's move on to the coding session. Here we learn the three techniques used in the paper. These techniques are used in many fields of research, so you never regret learning them. They are gradient descent method, Newton's method, and implicit differentiation. Believe it or not, the core of the implementation boils down to solving a constraint optimization problem like this. Here, we minimize a scalar function g, which is parameterized by model parameters theta. Then also, it contains the state variables x. Then these parameters and the state variables are interrelated in the nonlinear function f. In our manuscript, the objective function g is the error between the solution to the Richards equation and soil moisture data. And the parameters theta are the neural network parameters. And the state variables x are the soil water potential, basically the solution to the Richards equation. Then the nonlinear implicit functions, this is the constraint of this optimization problem is the Richards equation in our case. This is a very general setting, then maybe a little bit complicated for you. So I made a very simple toy problem for you. During the coding session, we used this simple toy problem to learn the three methods, gradient descent method, Newton's method, implicit differentiation. In this toy problem, the objective function g has two parameters, alpha and beta. Then also it has state variables, x1 and x2. Then these parameters and state variables are interrelated in the nonlinear function f, this one. Okay, so it's okay if you don't understand these equations now, it will be clear as we learn the three methods along the way. Okay, some of you are maybe wondering why I teach the three methods using a very simple toy problem rather than using real data set. Here are some of my answers to such a question. First, once we master the basics of the three methods, you can apply them to a variety of problems. Then also, I think when learning mathematical methods or models, it's very important to use synthetic data rather than real data at first, because by using synthetic data where we know the true solution for sure, then we can verify our implementation. If we use real data set, we never know the true answer for the inverse problem. So it's very difficult to verify our implementation. Also, when using synthetic data, we can learn how the methods behave, which would help us detect any bugs or potential new findings when applying them to real data set. Okay, so, well, I think this is not really the fastest way for research, but actually, I think this is the fastest way for publication, because if we test our methods on like synthetic data, then verify the implementation, then show it in the manuscript, reviewers would agree with that. So I highly recommend this type of approach when using new methods or new models. Okay, so let's move on to the coding session. Okay,
Um,
okay.
Toshi, just a quick question
Mhm.
before you move on to the coding part. Uh, the slide where you're showing that the objective function that is being constructed, uh, uh, yeah, maybe the slide before that, I think, where you
Okay,
introduced that yes. So you say that we are minimizing function g, which is a function of theta and state parameters.
yes.
And you say that we need to minimize or optimize because there's an error between the solution to Richard's equation and what we observe. Um, my question was little qualitative in the sense that what, according to you, might be causing such a error or bias as we model Richard's equation and what we see in real data? What exactly is not being captured in Richard's equation? Uh, yeah.
Uh, okay, so that's a good question. So I think you are talking about the model error, right?
Yeah.
Model error. Okay, so okay, this framework is limited in a sense that we have to assume some physical assumptions. Like for example, in the Richards equation case, we assume the water content is conservative, so the conservation of mass. Then also the water flux is the product of conductivity and the gradient of the hydraulic head or anything. Yeah, this is the assumption we have to make. But I mean, yes, yeah, so it just depends. Yeah, so if we want to loosen the assumption, yes, you can do that. But we have to define some physical models. Yes. Mhm.
Okay, and I think there's a question in Q&A, and it is, could you explain volumetric unit meter cube per meter cube? Does this mean it is unitless? I mean,
Well, yes, it's unitless. Yes, that's correct.
yeah, just to expand on that, maybe there are folks beyond hydrology. So meter cube per meter cube is just meter cube of water per meter cube of soil volume.
Mhm.
So just, yeah, go ahead, Toshi.
Okay, yeah, but it's very reasonable. Like if you are not familiar with like hydrology, like it's very normal, like what is the Richards equation, etc. But in this coding session, I will try to solving a mathematical problem that can be applied to any domains. So I hope you can learn some of the techniques I introduced in the lecture. Okay. Um, okay, so let's move on to the coding session. Um, During this coding session, we use the Jupyter Notebook file. I put the Jupyter Notebook file in the Google Drive folder, so please download it and open it on your local Jupyter Notebook environment if you are frequently using Python. But we are using Google Cloud for those who don't use Python regularly. We can do that later. During in the notebook, we only use NumPy and Matplotlib, so you don't have to worry about installing new softwares like machine learning software. I think if you are using Python, like you already installed NumPy. Yeah. Then I will introduce a machine learning framework, JAX, at the end of the coding session. Then, okay, during the coding session, you will be asked to replace the emoji in the notebook. I put them, in many places in the notebook. So then you will be replacing this emoji with correct mathematical equations or Python codes. In this way, I hope you can learn the three methods. Okay, so let's open the Jupyter notebook file. To do that, let me open the Google Club. Um, okay, I wait a little bit so that everyone have this tutorial notebook like on their computer.
Yeah, I was just going to sort of share that with everyone. So there's a Jupyter notebook which is there in the shared drive. You can open it in Google Colab, And I think I've gone through it, and Toshi has made it very simple. So I think if you follow along with him, there's great chance you'll learn more. So yeah.
Okay, so once you have this, screen on your like computer, yeah, please say, done or anything in the chat. I want to see how many people have this Jupyter notebook on your logo. Okay, sounds good. Okay, but anyway, so I'm not teaching you how to code in Python, but I filled most of the equations and Python codes in the notebook. So you, I think, don't really have to worry about the syntax of Python. So if you know the math, then I think you can do it. Then I will explain some of the Python concepts along the way as well. Okay, so let's begin with the coding session. Okay, so this is Jupyter Notebook on Google Cloud. This notebook is composed of many cells. This is a cell. This is a cell. Also, this is a cell. Then this is also a cell, etc. In order to run the cell, you can click this button. Then you can run the Python scripts inside the cell. It's still running. Okay, then I just finished importing these two libraries. Yeah, NumPy for like linear algebra calculation, then matplot, this library for plotting. We are only using these two libraries. Then okay, then if we want to run the cell using a key shortcut, then you can click Control plus Enter. So okay, Control plus Enter. Okay, so I rerun the cell. All right. So the first task for you is to replace this emoji with the right Python expressions. But before that, let me explain how to use Python a little bit. Okay, so before that, if you want to create a new cell, click B. Then in this way, you can create a new cell below this cell. If you want to create a new cell above this cell, you click A. Okay, here it is. Then if you want to delete the cell, you can click this button, right? Or you can click Control plus M plus D. Okay, Control plus M plus D. Okay, good. This is a little bit different from Jupyter Notebook though. Okay, so using this cell, let me a little bit explain how to use Python. In Python, you can compute some simple mathematical equations like this. 2 plus 3 equals 5, of course. Then multiplication, right? Then division. Then also you can compute 2 to 3. Okay, here I use the 2 asterisks. Okay, so these are the basic mathematical operations. But today we are using NumPy library, which is for linear algebra calculations. For example, using NumPy, we can represent a vector or matrices. Okay, as an example, let me try to solve a linear system. Ax equal b. Okay, let me define the solution first. Okay, let's say x is a vector, NumPy array, vector of 2 components, like 1 and 2. Okay, then I think then you can see the result by using a print function, print x. Okay, so this is a vector 1, 2, right? In order to define a matrix A, you can use a similar syntax, but in this case, this is a matrix. So we need 2 more like square brackets, 1, 2, and 3, 4. Okay. Then print A. Okay, so this is the matrix 1, 2, 3, 4. Okay, so sounds good. So then, okay, let's say we have A and we also have X. So we can compute B by matrix vector multiplication, which can be written by A times this at mark B, no, XA. Okay. Okay, this is the vector b. Okay, let me store this vector to a variable b. Okay, sounds good. Okay, now we can solve the linear system using NumPy. To do that, we use a function to solve a linear system, which is NumPy linear algebra. Then the first input is the matrix. Then the second argument is the right-hand side vector, which is b. Oh no, this is not here. Here it is. Okay, b. Oops. Oh no. Okay, I have to put solve here. Okay. Okay, right? Then okay, this is the solution x. Okay, I have to make sure this is correct. All right. Okay, this is the basic of NumPy libraries. Then I think I covered, yeah, I think all the like techniques, yeah, used in the notebook. So, but if you have any questions, just put them in the chat box. Yeah, I try to answer as many as questions during the coding session. Okay, so let me clean the Jupyter notebook by deleting them. Oops, this is not cool. Okay, so your first task is to replace this emoji with the right Python expressions to represent, to make a object called matrix that has the matrix of this guy. Okay, 1, 2, 3, 4. Okay, I'll give you 1 minute to do that. So, okay, please work on that. Once you're done, just put done in the chat box. Okay, 1 person. Okay, that's good. Okay. Okay, good. Cool. Okay. If you want to like define a matrix, NumPy array, then also then square bracket. We need 2 more square brackets. Then you can put the numbers here. Okay. Looks like many of you finished the first one. Yeah, this is just how to use NumPy libraries. So just have to get used to it. Okay, looks like most of you finished it, maybe. So, okay, this is the answer. So let me put this in here. Okay. Control and delete. Okay, let me run the cell. Okay, this is the answer to the first question. Yeah, 1, 2, 3, 4. This is good. Okay, so let's begin the real mathematics part. Okay, as I introduced before the coding session, we are solving a constraint optimization where we want to minimize a scalar function z, which are parameterized by the parameters theta, and also it has state variables x. Then these parameters and the state variables are interrelated in this nonlinear function f. Okay, so this is kind of complicated. So we are using a much simpler toy problem, then learn the 3 methods one by one. The first method is the gradient descent method. Okay, let me go back to the presentation slides to explain the concept. Okay, right, okay. Whoa, okay, here it is. Okay, the first method we learn is the gradient descent method to minimize a scalar function g. For simplicity, we ignore the nonlinear constraint f and focus on minimizing only the function g without any constraint. Here, we have this function g that has 2 parameters, alpha and beta. Then we fix the state variables, x1 and x2. We set these 2 state variables to be 1. All right. This is the problem setting. Our goal is to minimize this objective function g using a gradient descent method. Gradient descent step is described by this equation. In this equation, theta n is the solution or the parameters at the nth step of the gradient descent iteration. Gamma is a step size, also called learning rate in machine learning literature. Then the final term, this one is the gradient of the g function with respect to theta, evaluate at the current solution. The right figure shows how parameters approach to the local minimum point here from the initial guess of the parameters. We begin with some initial guess of the parameters x0, then gradient descent method updates the parameter using the gradient information. Then basically this goes to, where's the pointer? Okay, here, no. Let me, okay, there's a pointer here. Okay, we begin with the initial state, initial guess of the parameters. Then we update the parameters by the negative, by the gradient in the direction of the negative gradient direction, which is this direction. Then the next iteration, we have parameter x1, x2, x3, x4, etc. This is how gradient descent methods optimize the parameters. Okay, so you are going to implement this gradient descent method in the notebook to minimize this objective function. Okay, let's go back to the Jupyter notebook. Okay, so this is the program setup I already explained, but again, the function g has two parameters, alpha and beta, then also state variables x1 and x2. Actually, this objective function is called a Rosenbrock function. This is a kind of reference function to be used to test optimization methods. Then this function is known to have a global minimum where alpha is x1, beta equals x1 squared. This is because to minimize this function, this term must be 0. Then so that x1 equals alpha. Then also this term goes to 0 when beta equals to alpha squared, which is x1 squared. Yeah, so that's why this has the global minimum. Oh, then okay. Then during this coding session, we fix the state variables x1, x2 to be 1. Okay, so okay, this is the problem setting. So before implementing the gradient descent method, let's plot the Rosenbrock function. Okay, first, we set the state variables. As I said, we set the x1, x2 to be 1. So we run this cell to set the state variables, state test. Then this is the definition of the Rosenbrock function, which is g, function g. It has two input parameters. Then the first is the parameters theta, and the second input is state variables. We already defined the state variables for this setup. So I use the keyword argument to define to put the state test variable into this function g, but you don't have to really worry about that. So in this definition, x1 and x2 are extracted from the NumPy array state vector. But I have to mention that in Python, the first index is 0. I think if I remember correctly, in R, the first index is 1 maybe. But in Python, the first index is 0. So that's why we use 0 as an index here. Then, okay, alpha and beta are extracted from the parameters variable here. Okay, on 0. Okay, so your task is to implement Python expressions here. Okay, so in this expression, we are calculating the value of the function z. Okay, using x1, x2, alpha, and beta, etc. Yeah, basically what you are going to do is to change these mathematical expressions into Python codes. Okay. Then after that, we are creating many pairs of alpha and beta for plotting. So you don't have to worry about the detail of the code here, but basically this is the collection of alpha and beta for plotting. Then after that, we compute the Rosenberg function for a variety of alpha and beta pairs by running this code. You don't really have to worry about this as well. Then we can plot the function as well. Okay, so I will give you like 2 or 3 minutes to fill in this expression. So okay, let's do that. Also, it will be great if you put done comments into the chat once you're done. Okay, looks good. I guess if you are familiar with Python, this is just so easy. But if you are using R or maybe other languages, like, we have to, you need to maybe a little bit, more time. But okay, I hope this is quite simple. Like, I want to make sure everyone is on the same page. Okay, looks good. How about Devashish? Are you running the Jupyter notebook?
Yes.
Oh,
I was
really?
hoping I was hoping I'm not supposed to answer. So
Okay, I see. Okay, that's fine. Yeah, okay. So I hope you learn some of the methods as well. So, okay.
yeah.
Okay, looks like, okay, sounds good. Okay, let me type in the correct answers. Okay, so we just have to convert this mathematical expressions into Python code. So let me do that. We already get x1, x2, alpha, and beta in the definition of the function z. So we just have to type them in. X1 minus x alpha squared plus x2 times beta minus alpha squared, then squared. Okay. Okay, I think this is the answer. So is that correct? I think so, but I just want to make sure. Okay, but anyways, okay, I think this is correct one. So let me move on to running the codes below. Okay, let me run these cells to create many pairs of alpha and beta. Okay, this cell is evaluating the function for the set of the parameters. Then for plotting, okay, we are using a matplotlib. You don't have to worry about the detail, but this is the landscape of the function g. Okay, here the x-axis is alpha, the y-axis is beta, then the value of the function g is represented by different colors. This black region is very high value, which is about 10. Then this white region is very small area. You can see that, right? I also plotted the true solution of this optimization problem. That is alpha is equal to 1, then beta is equal to 1. Okay, you can see that global optima is in the white region, right? Okay, this is good. Okay, so our next goal is to get this global minimum solution using a gradient descent method. Okay, let's move on to the next part. Okay, so as I explained, the gradient descent step is described by this equation. Here, the theta is the parameters at n step, then gamma is a learning rate or step size. Then this nabla g, this is called nabla, by the way. Nabla g is the gradient of the function z. So because we don't use automatic differentiation, so we have to derive this gradient manually. Isn't that fun, right? Okay, so the definition of the gradient is this one. Okay, because there are 2 parameters, there are 2 entries in this vector. Okay, so the first one is the partial derivative of g with respect to the parameters alpha, and the second one is the partial derivative of g with respect to the parameter beta. Your task is to replace this emoji with the right mathematical expressions. Well, you don't have to put them into this notebook, but if you want to do that, you just double click this cell to open the markdown version of the notebook, then you can type them in, type some, mathematical expressions. I don't know this is correct, but okay, like this. Then click Shift plus Enter, then like this one. Then your task is to put the right mathematical equations into this vector. Okay, so after that, we have to convert these mathematical expressions into Python codes. This is the function for the gradient of the function g with respect to the parameters theta here, right? Okay, so these lines of the codes are exactly the same as before, but you have to, you will replace these emoji with the right expressions. Basically, you will convert the mathematical expressions you put here into the Python expressions. Okay, then after that, this line collects the two partial derivatives, this one, into a vector. Then that is the output of this function. Okay, then, okay, we have the gradient, right? So the next step is to implement the gradient descent method. Yeah, there are two functions, gradient descent step and gradient descent fit. Okay, gradient descent step implements a gradient descent method for only one step. Okay, so you will be replacing this emoji with the right Python expressions that describe this gradient descent step. Okay, then, okay, in this function, gradient is computed by the gradient function we define. So, okay, in this function, there are many parameters, many inputs here. The first one is the parameters, and this function is the function to be minimized. Then this grad function is the gradient of the function to be minimized. Okay. Okay, your task is to replace this emoji with the Python expressions to describe the gradient descent method in Python. Okay, then after that, the code evaluates the new value of the function g using the new parameters. Okay, then once you are done, in this gradient descent fit function, we are running the gradient descent method 300 times set by this and this parameter. Okay, what this function does is we are running this block of code until this expression is correct. Okay, this is the famous while loop. Okay, initially this index number I is set to 0. Then we increment this I at the end of each gradient descent step, like I equals I plus 1. Then once I is equal, I think, no, I equals to 300, the Python escapes from this while loop, then finish the function. Okay. Then after that, we are running this cell to run the gradient descent method, given the initial guess of the parameters. This is just a random parameter value I set. Then after that, we will plot the results. Okay, so I'll give you like 5 to 10 minutes to finish, complete the gradient descent method. So, okay, let's work on this.
Toshi, in between, I don't see any questions there, but I think I'm sort of assuming if uh, it's worthwhile sort to explain sort of the idea of gradient descent. I'm not sure if everyone is aware of what it is, but I mean, I can go ahead just to clarify a few things. So what Toshi is telling here is the best way to imagine or to understand gradient descent is imagine that you are at the top of the hill and you want to go to the valley, right? And if you want to go to the valley and you want to do it in the fastest way possible, then you'll search for the most steepest direction, right? Imagine that. And then that, when you sort of tell in mathematical language, is what is a gradient. You sort of find the direction by how you can reach the valley as quickly as possible. Now, what the step sizes, you can imagine that if you take one step, you're not going to go to the valley yet. So you have to take a number of steps. But then, the code is not a human being. We sort of realize when we are at the most bottommost point. So what the code, basically the GD fit, is doing is you're iterating that step again and again. So you're sort of walking to the valley, right? And you're saying you have to say, sort of give a criteria in which the code will know, okay, right now we are at the most bottom point. Um, so that's the overall bigger picture. And now the other thing is the gradient depends. So you take the gradient depending on the number of parameters present. For example, you can think, okay, there is one direction in which I'm going to go down, or maybe you have an undulating terrain, and then you have to go a little left and a little right and then down. So you have to measure your gradient in different directions. So here there's an alpha, there's a beta. So you're going in an alpha direction, you're seeing what is the gradient. Let me go in alpha direction, then a beta direction, and so on, such that you're minimizing and finding the most optimal value. So the question, the places where he has left it, where we need to fill in, is basically you need to you're trying to sort of provide the gradient expressions, if I can sort of give the hint. So you're sort of providing the expressions of what the gradient will be there. Yeah.
Yeah, thank you so much. Yeah, so much for the following up explanation. Yeah, that helps a lot.
Yeah.
Yeah, it's already 5 p.m., but I think we are finishing gradient descent method. Then yeah, take a 5 minutes break. Yeah. Okay, done, I think. Okay, sounds good. Sounds cool. Okay. Okay, I'll give you a little bit of hints. Okay, so to fill this one, this is the partial derivative of g with respect to the parameter of alpha. So what you are going to do is to compute derive the partial derivative of g. This is the function, right? With respect to alpha. This is a little bit complicated, but you can definitely this can be done on paper for sure. But if you are kind of lazy like me, then you can Google like derivative calculator. Then this software is basically computing the analytical derivative automatically. So what we can do is to just copy this expressions, then yeah, put them into the this software. Okay, no. I think we have to then take the derivative with respect to alpha like this. Okay, this is in fact the answer. But I'm not really recommending this way because we should be able to derive the partial derivative by ourselves. But this is a good way to verify our derivation, yeah, in practice as well. Okay, so then for the partial derivative of g with respect to beta, you can just change this to beta, then run the program as well. Then okay, this one's much simpler than the one before, or something like this. Okay, but let me fill in with the right expressions. I already did that, of course. So let me. By the way, I will share the completed notebook at after the lecture, so no worries. This is the answer, and the other one is this one. Okay. Okay, this is the right mathematical expressions for the partial derivative of this one and this one. Okay, so please convert this into the Python expressions to compute the partial derivative g with respect to alpha and beta as well. Okay. Okay, so let me do that. Okay, minus 2 times x1 minus alpha minus 4 times alpha times x2 times beta minus alpha squared. Okay, this is the first one, and the second one is like this way. Okay, here we go. I think this is correct. Let me double check. Okay, looks fine. Okay, we run the code here to define the derivative of the function g with respect to the parameters theta. Okay, so the next task is to define the gradient descent step. Okay, new parameter, which is the theta n plus 1 equals theta n minus gamma times gradient. So the current parameter is params, right? Then, okay, the gamma is learning right here. So instead of gamma, we use a variable called learning rate. Rate times gradient is computed by this expression. Gradient equals to grad function. Then grad function is in fact used here, which is the input of this GD fit function. Okay, we will put the definition of the gradient function into this one. Okay, so gradient. Okay, then run the code. Here we go. Okay, so we can run the gradient descent method by beginning with some initial guess of the parameters. In this case, I set this to be -1 plus and 2.5, but you can choose other parameters as well. Okay, then we use this GD fit function. Then the input to this function is the initial guess of the parameters, params in, which are defined in this expression. Then g is the function to be minimized, and d theta is the function we defined in this cell to compute the gradient. Okay. Right, let me run this code. Okay, it's done. Okay, let's plot the result. Okay, you don't have to worry about this cell, but basically this cell is creating a data for a reference line for the linear convergence. You can see what I mean quite soon. Okay, this is the result for the gradient descent method. Here, the x-axis is the number of gradient descent iterations. We run gradient descent method 300 times. So that's why this is the end of the gradient descent method. Then the y-axis is the value of g in terms of log scale. So you can see the result is shown by the blue line. So you can see the function value is quite high at the initial estimate, but decreases kind of monotonically, right? Like this one. Then this orange line shows the reference line for the linear convergence. If we are interested in the rate of convergence, please refer to the Wikipedia on that. But in terms of theory, gradient descent method is known to be known to have a linear convergence property. So this graph or figure shows that our gradient descent method is really linearly decreasing the objective function z, which align with the theory, which is good. Okay. Then looks good. Okay, next, let's plot how the parameters approach the global minimum. Okay, so you don't have to worry about the detail of this, Python expressions. But what this cell is doing is to get alpha and beta value from the output of the GD function, the GD fit function here. Okay, this is the list of the parameters along during the training. Okay, let's run this one. Okay, then this cell plots the result. Here we go. We began with the initial guess of the parameters, which is here. Then during the gradient descent method, the parameters are changing from here to here to here, etc., etc. You can see that it took many iterations from here to here because this is because the gradient of this white region is very small. So it's very difficult for the gradient descent method to move from here to here. Okay, but I mean, it looks good. So finally, let's make sure the final parameters are correct, right? We know that for this simple problem, we know the answer is alpha equals beta equals 1. So let's make sure that is the case. This is the final parameters we get from the gradient descent method. So let's run the cell. Okay, this is the value of the alpha estimated by the gradient descent method, which is very close to 1, then beta as well. So this is good. Okay, this is the basic of gradient descent method. So I hope you learned something from this notebook so far. Okay, so it's already 5:10 in California. So okay, so let's take a 5 minutes break. Then the next topic we learn is the Newton's method to solve nonlinear equations. Okay, so the next method is Newton's method to solve nonlinear equations. First, let me explain how to solve a function of like single variable f of x equals 0. In the right figure, the x, okay, let me pull up the pointers again. It disappears again and again. Okay, here it is. Okay. In the right figure, the function f of x is shown by the blue curve like this. The goal of the Newton's method is to update the solution x iteratively to get the root of the nonlinear function f of x equals 0. This is the root of the f of x equals 0. Okay, so in Newton's method, the solution xn is updated by a so-called Newton step s, like this. Then s is computed by this mathematical expression. This looks kind of complicated, but in the right figure, the Newton step is the base of this triangle made by the tangent line of the function f at the current solution and the y and the x-axis. Basically, we update the solution by this Newton step until the solution really gets closer to the root of the problem. Okay, so this figure shows how the Newton's iteration works. We begin with an initial guess of the solution x0, then update the solution by the Newton's step until the solution satisfies the equation f of x equals 0 up to a Newton tolerance, which is a very small number. Let's say 10 to -8 or -12. Okay, now this is the second iteration. This is the third iteration. The solution gets closer and closer to the root of the f of x equals 0, right? Okay, this is how Newton's method works for a function of a single variable. But what we are dealing is a function of multi-variables. Like in our case, the number of the variables is just 2, but in practice, like 100 or 1,000 or more maybe. So in such a case, Newton's method have a very similar mathematical expressions. The first one is almost the same, but in this case, the x and s are vectors because there are multiple variables in the function f. Then the Newton step s is computed by the value of the function f at the current solution, and the Jacobian matrix, basically the derivative of f with respect to the variables x. All right. Then, okay. This is how Newton's method work. But in the coding session, we are solving much simpler problem like this one. So here, there are only 2 nonlinear equations. we solve these two nonlinear equations at the same time by using this Newton's method. Here, we fix the parameters alpha and beta. They are 1. Instead, we solve these nonlinear equations in terms of x1 and x2, right? Okay. Okay. In the coding session, you are asked to derive the Jacobian matrix, which is the derivative of the function f of x. Then implement the Newton's method. Okay, let's go back to the coding notebook. Okay, this is the problem setup. Again, the function f has two parameters, alpha and beta, but we set these parameters to be 1 for simplicity. Then we are solving these nonlinear equations in terms of x1 and x2. All right, this is the Newton step. Then this is, okay, Newton step S can be computed by Jacobian matrix like this. But rather than using the inverse of the Jacobian matrix, we move this to the left by multiplying the Jacobian matrix itself from the left. We are solving linear system like this. This J is the Jacobian matrix. The differential of the Jacobian matrix is like here. This is a matrix. Then this term is the partial derivative of the first component of the function f with respect to the first state variables x1, etc. You will be deriving the Jacobian matrix by yourself. Okay. Then after that, you will convert these mathematical expressions into Python expressions here, right? Oh no, that's not correct. Okay, this is the definition of the nonlinear equations. So what you are going to do is to transform this mathematical expressions into Python expressions here. Then f1 and f2. Okay. Then we stack these numbers into a vector like this. Then after that, you will put these mathematical expressions into Python expressions here. This is the J11 component of the Jacobian matrix here, this one. This is J12 is J12 is this one, etc. Okay. Then this is the function to run the Newton's method. Okay, there are many input parameters, but this is the state variables. This is the additional arguments that are needed in the function evaluation. In this case, they are parameters, alpha and beta. This function is the function f. Then this Jacob function is the definition of the Python function for the Jacobian evaluation. Okay, this is the tolerance of the Newton's method. Basically, we are iterating the Newton's method until the f of x is smaller than this value using this while loop. Initially, the error is set to infinity, but as time goes, this error becomes really small. Then once this number is smaller than this tall number, which is 10 to negative 12 in this case, then we are escaping from the while loop. Okay, in this block, you are implementing this Newton step. Okay, you have to, this is the right-hand side of the Newton system. This is the Jacobian matrix evaluation. Then you are solving the linear system to get the Newton step. Then we update the state variables using the Newton step, dx in this case. Okay, then we evaluate the error by the maximum value of the absolute value of the function f. This is quite normal, yeah. All right, so then later we test this method by setting the parameters to be 1 and 1, and the initial guess of the state variable is also 1 and 1, but later we will test another initial guess as well. I will talk about that later. Okay, so let's work on this. Okay, I will give you like 5 to 10 minutes to do that. Okay, so there is a question in the chat. So Newton's method is basically an iterative method. Okay, the answer is yes. Yeah, to derive these Jacobian matrix, you can use the derivative calculator like this website. But I think this one, the computing the derivative is very simple. Yeah. Okay, let me put this one first. Okay, this one is the derivative of this one with respect to the state variables x1. So this is very simple. This is going to be just beta. Beta. Then for this entry, this is going to be negative 2x2. Then for this one, we take the derivative of this one with respect to x1. So this is going to be just 1. In the same way, this is going to be 2. And in this function, we are evaluating the function f. So we are going to transform these mathematical expressions into Python expressions. Okay, this is going to be beta times x1 minus x2 squared plus alpha. Then the second component is this one. So this is going to be x1 plus x2. Oh, by the way, Devashish, can you see my cursor, right?
Yes.
Okay, that's good to know. Okay, I just want to make sure. Okay. Oh, I forgot to put 2 here. Okay. Okay, this is it for the function f. Also, by the way, once you're done, please put down in the comment or chat box. Oh, okay, good. Okay, good to hear. Yeah. Okay, good. Okay. I hope so far the things are not too difficult, but actually the last part of the notebook is kind of complicated. So I hope, yeah, yeah, many of you can, understand, the topic, but, even after the lecture, you can read through the notebook to learn the methods. Yeah. Actually, honestly, like it took more than a month for me to understand all the techniques I introduced here during my PhD. So it's quite normal, like if you don't understand all the techniques in these 2 hours. So no worries. Okay, so let me put them in the right expression. Okay, this is beta. Then this is 1, 2 is minus 2 times x1 minus 2 times x2. Then this is 1 and this is 2. Okay, here we go. This is the answer. Okay, by the way, so just make sure if you have not done, please make sure write them these Python expressions into your notebook as well, so that we can run the code together later. Okay, this one and this one. Okay, so here is the Newton's method. Okay, what we are going to do is to solve the Newton system, which is this linear system. The left-hand side is a Jacobian matrix, and the right-hand side is the residual of the, this is f of x, yeah. So this is going to be J, the F, right? Then Newton's step is state minus dx. Dx is the Newton step, right? Okay, looks good. So, okay, so let me set the parameter alpha and beta to be 1. Then this is the initial guess of the state variables, x1 and x2. Then this expression runs the Newton's method. Okay, so you can see some, these sentences. Okay, these sentences are a result of these Python expressions. So this prints the current value of the error term. Error is evaluated here. You can see the error decreases rapidly. This is so-called quadratic convergence. You can see the number of the exponent became doubles, for each Newton's iteration. This is a nice property of Newton's method. So we just want to make sure the Newton's method behaves correctly. If you solve different nonlinear equations, you will see very different behavior maybe. So yeah, but it's very important to check the convergence rate of the Newton's method every time you use the Newton's method. Yeah. Okay, so let's confirm the final solution is very close to the analytical solution. So actually for this nonlinear equations, we can manually manually derive the solutions, given the parameters alpha and beta are 1. I already did that. Then there are actually 2 solutions. The first solution is x1 is 5 minus 2 times square root of 5, and x2 is this number. And the second equation is 5 plus 2 times square root of 5. And this one is also kind of a little bit different from this one. Let's check if our solution is close to this solution in this case. All right, okay, this one is the solution obtained by the Newton's method. Then this one is the analytical solution I derived. You can see these numbers are very close to the one we got by using the Newton's method. That's good. But the point is, if we use a different initial guess of the state variables, x1 and x2, we might get a different solution. So one of the property or disadvantage of the Newton's method is the final solution is a little bit sensitive to the initial guess of the parameters, initial guess of the state variables. So if we use this 10 and negative 2 as the initial guess of the solution, yes, okay, then here we go. Okay, this is the solution we get given this initial guess of the solution. This is totally different from the one I showed before, but this is very close to the second analytical solution. Okay, so this is the property of Newton's method. So we have to choose the initial guess of the solution very carefully. Otherwise, you might fall into a different solution you want. So, but in practice, especially when solving the partial differential equations, usually there is a single solution. But if you happen to find multiple solutions, then you definitely should write a paper. Yeah, that's a good finding actually. So, okay, that's good. Yeah, for the Newton's method. Okay, so let's move on to the final part of the notebook, which is solving constraint optimization problem using implicit differentiation. Okay, let me go back to the PowerPoint slide. Okay, here we go. Okay, so now we are finally ready to solve the constraint optimization problem. where we want to minimize the function g, where the state variables x are constrained by the nonlinear equation f equals 0. When we learned the gradient descent method, computing the gradient was very simple because there was no constraint term like f. Then when we learned the Newton's method to solve nonlinear equations f, there was no minimization problem g. So that was simple as well. But now we combine the two techniques to solve this constraint optimization problem. When in the previous section, the gradient computation was very simple because there was no constraint. But now we need to take into account the effect of x through the nonlinear system, nonlinear constraint. To do that, we compute the total derivative of the function g with respect to the parameters theta using the chain rule. There are two terms here. The first term is the direct effect of the parameter theta, and the second term is the indirect effect of the parameter theta through the state variables x. This is based on the chain rule. You see, this is the dg dx times dx d theta. This term is called sensitivity. Because this matrix shows the effect of the parameters on the state variable x. Computing these dg d theta and dg dx is relatively simple. Actually, we already calculated dg d theta in the gradient descent method section. Then this one is also easy to derive, but deriving dx d theta is not simple. So this is where implicit differentiation comes into play. There is a mathematical theorem called implicit function theorem. The theorem says that at the solution of the nonlinear systems, the state variable x is a function of the parameters theta at the solution of the nonlinear systems. So we can rewrite these nonlinear equations into this equation where the state variables x is a function of parameters theta. Then we can differentiate the function f with respect to theta using the chain rule. This is basically the same way when we derive the total derivative. So df dx times dx d theta plus df d theta. Okay, so the sensitivity is here. So to get this sensitivity, we move this term to the right, then multiply the inverse of this Jacobian matrix. Then we get the sensitivity, right? Okay, then we put these expressions into this total derivative expression to get the last equation. Okay, this is the formula to compute the total derivative of g with respect to the parameters theta. From here, there are two ways to evaluate this total derivative. Okay, this slide is extremely important because this slide explains how to compute the total derivative efficiently when the number of the parameter is large. For example, when integrating the neural networks. Actually, this method, there are two methods to compute this total derivative. The first method is called direct sensitivity method, and the second method is called adjoint method. The difference between the two methods is the order of calculation. In direct sensitivity method, we compute this term first. Then in the adjoint method, we compute the pink bracket first. In fact, if you are using machine learning, probably you are familiar with the term called backpropagation. Backpropagation is a special case of the adjoint method. So we are using adjoint method to compute the total derivative because that's more efficient when the number of the parameter is large. This is very important. Okay, so let's explain the direct sensitivity method first. As the name suggests, direct sensitivity method computes the sensitivity first. This is the expression to compute the direct sensitivity method. So then in order to get this one, rather than inverting this Jacobian matrix, we just move this to the left to get this equation. You might notice this is the Jacobian matrix we already derived, and this is a matrix, dx d theta. Then also this is also a matrix. So this equation is matrix times matrix equals matrix. So to solve this equation, we have to solve linear systems multiple times, which is not really efficient when the number of the parameters is large. So that's why we use adjoint method, where we compute this term first. To do that, we define a so-called adjoint variable P to be this term. The transpose of the adjoint variable is this pink bracket term, right? Then if we multiply the Jacobian matrix df dx from the right, we get this expression. Then by taking the transpose of both sides of the equation, we get this equation. This equation is called adjoint equation. This is the transpose of the Jacobian matrix. Then this is because the function g is a scalar function. This is also vector. So this adjoint variable p is a vector as well. So this adjoint equation is just a linear system. So solving the adjoint equation is much efficient than the direct sensitivity method when the number of the parameter is large. So that's why we use adjoint method. So then finally, then after we get the adjoint method, adjoint variable, we put the adjoint variable into the this total derivative expression to evaluate the total derivative. This is the equation we get finally. In the coding session, we are focusing on solving this toy constraint optimization problem. This is basically the combination of the function g and function f we already discussed in the notebook. Then here we are using a gradient descent method to minimize this function g under the constraint of f. So to do that, we need the gradient dz d theta. So in order to compute this one, we need this value, but we already computed this value. Then we have to solve the adjoint equation to get the adjoint variable. But okay, so what we need is the derivative of g and f in terms of theta and x. In fact, we already derived this term and this term already. What we have to derive additionally is this term and this term. Okay, that's what we are going to do. Okay, so let's go back to the notebook. Oh, it looks like we are running out of time, so let me go through a little bit faster. Okay, this is the problem setup. This is a nonlinear constraint, and this is the function to be minimized. In this case, actually, we have the analytical solution as well. This is the analytical solution. Our goal is to minimize the function g using a gradient descent method. Okay, so okay, although we already defined the function g, but because of some technical issues, we have to redefine the function g as well. So let me do that for you guys. So this is just x1 minus alpha squared plus x2 times beta minus alpha squared. Okay, here we go. Okay, so I'll give you 5 to 10 minutes to derive the fill in the emojis here. Basically, what you're going to do is to derive the derivative of this one and put them into Python expressions here. Then this one as well. Then after that, we combine all of the functions we defined, then implement the adjoint method. Just for reference, I implemented direct sensitivity method as well. Okay, so but please focus on this one. So okay, let's do this. Yeah, Deva says, yeah, you're right. Yeah, we are kind of running out of time. Yeah. Okay, there are two questions in the Q&A box. The first question is this the Newton-Raphson's method? Yes, that's correct. Which other algorithms are generally application for nonlinear problems? Okay, in terms of solving nonlinear systems, then other approach is a Richardson iteration. Basically, just you don't in the Richardson iteration, you don't have to derive the Jacobian matrix, etc. But I think Newton's method is the kind of the golden standard way to solve nonlinear equations. That's very fast. Then also, I have to mention that because the Newton's method is a little bit sensitive to the initial guess of the solution, we need to implement a so-called globalization techniques to kind of stabilize the Newton's method. So I implemented line search in my manuscript as a globalization technique. But I'm sorry, but I don't have time to dig into such a detail, but I will share some resources at the end of the lecture, so no worries. Okay, then the second question is, can the Jacobian matrix be tweaked to accommodate a bigger matrix, say a 50 row by 12 column matrix and beyond? Yes, of course. But of course, it's very difficult to derive such a big Jacobian matrix manually. So, but actually people do that. Yeah, but in practice, I personally prefer to use automatic differentiation to derive the Jacobian matrix. I'll talk about that later, a little bit though. Yeah. Okay, so let me start typing in the right expressions. Okay. This one is going to be 2 times x1 minus alpha. And this one is going to be beta minus alpha squared. Okay, here we go. Oh, shit. Sorry. Okay, it should be. Okay, here we go. Then this is going to be 2 times x1 minus alpha. Then this is going to be beta minus alpha squared. Squared. Okay. Okay, then this one is going to be this 0, 0, 2 times alpha plus x1 times beta minus x2, and this is going to be 2x1 x1 beta plus alpha minus x2. Okay, here we go. Oh no. Okay. Here we go. Okay. No worries, I will share the completed tutorial later. So, okay, this is going to be x1, 0.0, and 0. Okay. Okay, so I don't have a lot of time to describe this one, but okay, first we begin with the initial guess of the solution. Okay, this is the function to compute the total derivative of g with respect to the parameters theta. Okay, first we have to solve the nonlinear equation, so we use the Newton's function we derived. Okay, then here we compute this term, and okay, dx, then okay, dx, df, d theta. Okay, here we go. Then this is the adjoint equation. So this is going to be the x transpose. Then this is going to be the negative of dg dx transpose. Then finally, this is going to be, this is the direct effect of the parameters theta, and this is the indirect effect computed through the adjoint variables p. Df theta. Okay, here we go. Unfortunately, I don't have time to explain this section, but the point is, after we derive the analytical derivative using the adjoint method, we really have to verify it by a finite difference method. So to do that, this is going to be the function to be differentiated, which is g. Then this is the total derivative function we just derived, this theta. So if you run this code, okay. This is the x1, x step. This is y1. Okay, here we go. Okay, you can see the nice figure here, right? The x-axis is the finite difference method, step size of the finite difference method, and the y-axis is error between our analytical derivative and the finite difference method based derivative. You can see the error decreases linearly with the decreasing step size, which is a good sign. So if our implementation was not correct, then we would get a very different figure. For example, if I put a point, 1 point now here like this, then we get very different figure. So it's very important to have this type of figure. Yeah. So even if you use automatic differentiation, I highly recommend you compare the derivative by automatic differentiation with finite difference method, because it tells you a kind of the nature of the problem, then helps you kind of come up with a new transformation rule for the parameters in your problem. Okay, so now we have the gradient based on adjoint methods, so we can apply the gradient to the gradient descent method. Okay, so I just run the code. Here we go. You can see the objective function g is linearly minimized by a gradient descent method. That's pretty good. Also, this is the final value of the parameters we get. Then this is analytical solution, right? You can see these values are really similar. So we were able to minimize the objective function g under the constraint f. Okay, so that's it for the notebook. Sorry for the kind of rushing up at the end of the lecture, but let me go back to the slides. Okay, this is the explanation for the finite difference method. Okay, so let me quickly introduce the machine learning framework called JAX. Okay, JAX is very similar to PyTorch and TensorFlow. So it comes with automatic differentiation. The interface is very similar to NumPy. So JAX uses a functional programming style. So it has many transformation functions for automatic differentiation, batching, and compilation. Finally, the same codes can run on CPUs and GPUs. If you are familiar with other machine learning frameworks such as PyTorch, you don't really have to switch to JAX, because what you can do with PyTorch can be done by JAX as well. The other side is also possible, is also the case, so no worries. But if you are interested in the difference between JAX and Julia, or maybe PyTorch, I just recommend the blog post by Patrick. He's an expert in JAX. JAX really automates and simplifies the implementation of the adjoint method. And all the implementation I described in the notebook. For example, this slide shows a comparison between NumPy and JAX when defining the derivative of the function z. So we derive this function in NumPy, but if we use JAX, we only have to write a single line of code using the grad function from JAX. This is based on like automatic differentiation, which is really nice. How about the adjoint method? In JAX, we just have to define the direct sensitivity method for the Newton's method. In this code, we define the Newton's method, define the custom JVP rule, which is Jacobian vector product, which is basically equivalent to direct sensitivity method for the Newton solver. Then as for the adjoint method, JAX automatically converts this JVP rule into VJP rule, which is equivalent to adjoint method. So you just have to define this JVP rule in JAX. How about how to implement this approach for time-dependent PDEs like the Richards equation? The answer is to just implement the JBP rule for the Newton's method. Then JAX takes care of everything else. We share the JAX code for the manuscript in this repository. So yeah, if you are interested, please play around the code. Okay, finally, I will share some resources. If you are not sure about basic calculus and linear algebra, I recommend these resources. Then the last textbook is a little bit advanced, but if you can read this textbook, yeah, you can read papers by applied mathematicians. Then these are also resources for like solving PDEs, which I couldn't explain in the tutorial. Also, there is a good textbook on optimization, Newton's method. And if you are interested in the advanced topic for PD constraint optimization method, I recommend the latest review paper written by Gattas and Wilcox. This is a good review paper. Basically, yeah, my PhD research is based on the last review paper, in fact. Okay, so I kind of rushed to the end. But thank you so much for your attention. Then please don't hesitate to contact me if you have any questions. I mean, you can contact me through the email. Also, I have a Twitter or X account here. Then also I have homepage and GitHub repository. So okay, that's it for my lecture. Then thank you so much for your attention.